Machine learning, ML, is coming into its own, with a growing recognition that ML can play a key role in a wide range of critical applications, such as data mining, natural language processing, image recognition, and expert systems. ML provides potential solutions in all these domains and more, and is set to be a pillar of our future civilization. The supply of able ML designers has yet to catch up to this demand. A major reason for this is that ML is just plain tricky. This machine learning tutorial introduces the basics of ML theory, laying down the common themes and concepts, making it easy to follow the logic and get comfortable with machine learning basics. What is machine learning? So what exactly is machine learning, anyway? ML is actually a lot of things. The field is quite vast and is expanding rapidly, being continually partitioned and sub-partitioned ad nauseum into different subspecialties and types of machine learning. There are some basic common threads, however, and the overarching theme is best summed up by this oft-quoted statement made by Arthur Samuel way back in 1959, "Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed." And more recently, in 1997, Tom Mitchell gave a well-posed definition that has proven more useful to engineering types. A computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T, as measured by P, improves with experience. A computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T, as measured by P, improves with experience E. Tom Mitchell, Carnegie Mellon University. So if you want your program to predict, for example, traffic patterns at a busy intersection, task T, you can run it through a machine learning algorithm with data about past traffic patterns, experience E, and, if it has successfully learned, it will then do better at predicting future traffic patterns, performance measure P. The highly complex nature of many real-world problems, though, often means that inventing specialized algorithms that will solve them perfectly every time is impractical, if not impossible. Examples of machine learning problems include, is this cancer? What is the market value of this house? Which of these people are good friends with each other? Will this rocket engine explode on takeoff? Will this person like this movie? Who is this? What did you say? And, how do you fly this thing? All of these problems are excellent targets for an ML project, and in fact ML has been applied to each of them with great success. ML solves problems that cannot be solved by numerical means alone. Among the different types of ML tasks, a crucial distinction is drawn between supervised and unsupervised learning. Supervised machine learning, the program is trained on a predefined set of training examples, which then facilitate its ability to reach an accurate conclusion when given new data. Unsupervised machine learning, the program is given a bunch of data and must find patterns and relationships therein. We will primarily focus on supervised learning here, but the end of the article includes a brief discussion of unsupervised learning with some links for those who are interested in pursuing the topic further. Supervised machine learning. In the majority of supervised learning applications, the ultimate goal is to develop a finely tuned predictor function HX, sometimes called the hypothesis. Learning consists of using sophisticated mathematical algorithms to optimize this function so that, given input data X about a certain domain, say, square footage of a house, it will accurately predict some interesting value HX, say, market price for said house. In practice, X almost always represents multiple data points. So, for example, a housing price predictor might take not only square footage x1, but also number of bedrooms x2, number of bathrooms x3, number of floors x4, year bill x5, zip code x6, and so forth. Determining which inputs to use is an important part of ML design. However, for the sake of explanation, it is easiest to assume a single input value is used. So let's say our simple predictor has this form, wherein are constants. Our goal is to find the perfect values of and to make our predictor work as well as possible. Optimizing the predictor HX is done using training examples. For each training example, we have an input value x_trained, for which a corresponding output y is known in advance. For each example, we find the difference between the known, correct value y, and our predicted value HX_trained. With enough training examples, these differences give us a useful way to measure the wrongness of HX. We can then tweak HX by tweaking the values of and to make it less wrong. This process is repeated over and over until the system has converged on the best values for and. In this way, the predictor becomes trained, and is ready to do some real-world predicting. machine learning examples. We stick to simple problems in this post for the sake of illustration, but the reason ML exists is because, in the real world, the problems are much more complex. On this flat screen we can draw you a picture of, at most, a three-dimensional dataset, but ML problems commonly deal with data with millions of dimensions, and very complex predictor functions. ML solves problems that cannot be solved by numerical means alone. With that in mind, let's look at a simple example. Say we have the following training data, wherein company employees have rated their satisfaction on a scale of 1 to 100. First, notice that the data is a little noisy. That is, while we can see that there is a pattern